right, this is Physics Chapter 10, Lecture 2. The first problem we're going to work from your textbook is on page 338. And we are starting at the top of page 3 on your notes. So to go over what's some of the things that are on your notes, we're still talking about springs here. So a spring at amplitude, so that's a spring at its furthest pulled out. Okay, so if a spring is at equilibrium and you pull it, all right, so we have our spring and then we have a mass hooked to that spring. When we pull it down to its furthest point, that's amplitude, and then you let it go. Potential energy at that point is at its maximum. Kinetic energy is 0 because the velocity is equal to 0 at amplitude because it's changing directions. It gets to the bottom and goes back up, changing directions there, so velocity is 0. Now at equilibrium, so that's that as it goes up and down, that middle point, then potential energy is 0 there. Kinetic energy is at its maximum because your velocity is at its maximum at that point. So there's some 4 equations that govern spring energy that you need to memorize. So potential energy is 1/2 k delta x squared. So delta x is just the distance from equilibrium at whatever point in time you're interested in. Kinetic energy is just like kinetic energy that we used in chapter 8, 1/2 mv squared. And then the total energy is 1/2 k and then times the amplitude squared. That amplitude, of course, is that maximum distance that the spring has been pulled from equilibrium position. And then you have the energy equation. Total energy is going to equal to potential energy plus kinetic energy. All right, so let's work 3 on-your-own problems that involve these energy equations with springs. So 10.6, how much work is required to stretch a spring, and it gives a K of 3,412 newtons per meter, 34.5 centimeters. All right, so we have so we've got 10.6 here. We are on page 338. So work is total energy. So that's just going to be 1/2 k times the amplitude squared. So that would be 1/2. K is 3,412. So that's a really strong spring. And then the distance, we're going to need to put that in meters. So that'd be 0.345 meters. And then don't forget to square it. That's an easy thing to forget. So that's going to be 203.1 joules. All right, let's try 10.7. It's right underneath 10.6. So that one says a 61.2 kilogram mass, pretty heavy, is placed on a spring set into simple harmonic motion by pulling it 23.1 centimeters from its equilibrium position. If the maximum speed of the mass is 3.4 meters per second, what is the spring constant? All right, so in this problem, we are at maximum speed. Okay, they've given us the maximum speed. That means that we are at equilibrium. Okay, so potential, if we have our energy equation, total energy is equal to potential energy plus kinetic energy. We know that kinetic energy, we're at the maximum, and that means that we're at equilibrium, so potential energy is 0. All right, and it's 0 because we are at equilibrium. All right, so we have 1/2 k a squared is equal to 1/2 mv squared. So we want to know the speed. All right, so, well, the halves cancel out since we have those on both sides. So algebraically, for solving for velocity, we would know that velocity squared is going to be k a squared over m. So then velocity would be the square root of that. So that's going to be the square root. K is, oh, I'm so sorry, we're solving for the spring constant, so I apologize for that. Let's redo that. All right, solving for the spring constant. So similar algebra, K is going to be mv squared over a squared. All right, so K is going to be, the mass is 61.2 kilograms. All right, sorry if I made you erase a little bit there. 3.4 meters per second. All right, got to square that. And amplitude 0.231 meters. Okay, we've got to change that to meters. Don't forget to square that. So if you put that in your calculator and don't mess up, you'll get 13,258.2 newtons per meter. All right, that's a pretty strong spring. Okay, so let's do 10.8 and then we'll move on to pendulums. All right, 10.8 says a 54-gram mass is placed on a spring if it's displaced 5 centimeters from its equilibrium position. Right, if it's displaced 5 centimeters from its equilibrium position, how fast will it be traveling when it's only 2.5 centimeters away from equilibrium? So we are neither at equilibrium or amplitude, so nothing cancels out here. Whereas in the last problem, potential energy canceled out. Potential energy was 0. Nothing is 0. So we have 1/2 Ka squared is equal to 1/2 K delta X squared plus 1/2 mv squared. Well, since you have a half in every term, we can cancel those out. And this time we are solving for velocity, so I'll try not to make that mistake again. So algebra-wise, if we pull this part to the left and then divide by the mass, we would have v squared is equal to Ka squared minus K delta X squared over the mass. All right, so v squared is equal to, okay, K is 15 newtons per meter, a very weak spring. The amplitude that it was pulled back would be 0.05. We're changing from centimeters to meters. Don't forget to square that. All right, we're right here. Delta X, our position of interest, is 2.5 centimeters, so that's 0.025 meters. All right, and then divide that by the mass, which is 54 grams. We've got to change that to kilograms, 0.054 kilograms. So our velocity squared, if you go through the math there, is 0.52. Be meters squared per second squared. And then we just want to, don't forget to take the square root of that number. So velocity is going to be the square root of 0.52, which is 0.721 meters per second. All right, so that does it for springs. Let's talk a little bit about pendulums, or pendulums, however you like to say it. we are moving on to page 4 of your notes. Okay, so for a pendulum, and I'm going to link a video in the description box for you to watch someone calculating the period of a pendulum. But with a pendulum, of course, we have a mass on some sort of attached to some sort of string or chain or whatever. All right, this would be like the ceiling or the bar that it's attached to. So for a pendulum, if you were to pull it out, okay, as long as the angle you pull it is less than 20 degrees, then it exhibits simple harmonic motion. So period is independent of amplitude as long as it's less than 20 degrees. If you get more than 20 degrees, you're looking into more of circular type motion, okay? So the period of a pendulum is the time it takes, let's say you pull it out this much, for one cycle. So it would go that and then come back, and it's the time it takes to get back to its original position. So voot, voot, that's the time. Okay, so we do have an equation for that you need to memorize. It is the period, so that's just time, is equal to 2 pi times the square root of the length over gravity. So the period of a pendulum depends on its length. Let's look at on your own 10.9. All right, so we are looking at page 342. All right, that says, what is the period of a pendulum whose length is 2.5 feet? All right, well, that's a straight plug-in problem. You just need to remember, since we're in feet, to have gravity be 32. All right, so 2 pi times the square root of 2.5 feet over 32 feet per second squared. That's 1.76 seconds. So for a 2.5 foot pendulum, that's pretty long. It takes 1.76 seconds for it to get out and back again. All right, to get out once, it would be half of that. To get to straight up and down, it'd be a fourth of that number. All right, and then finally, 10.10. If a pendulum has a period of 0.45 seconds, what is its length? All right, so algebraically here, we are just solving for length. All right, let's pull the, just like before in the springs, let's pull the 2 pi underneath t. Let's square both sides. To lift the radical, so we'd have t over 2 pi all squared is equal to L over G. And we are solving for L. Multiply both sides by G. L is equal to G times t over 2 pi all squared. All right, so let's plug the numbers in. It doesn't say whether we are in meters or feet, so I'm going to presume meters on this one. So 9.8. All right, t is 0.45. And then 2 pi is 2 pi. Don't forget to square it. That's an easy thing to forget. And you will have a length of 0.05 meters. If it asks for centimeters, then it'd be 5 centimeters, but it doesn't say anything like that. All right, so you are capable of doing all of the review questions and practice problems from Chapter 10. All right, so what would be the review questions that would go with this lecture? On page 349 would be 7 through 10. The practice problems on page 350, you can do 6 through 10. All right, so that does it for Chapter 10. And I will talk to you next time.